Would you say that MDPs are the most generally applicable planning formalism? And someone else asked, what are the limitations of MDPs? Does anyone remember what the hell an MDP is?
It's a Markov decision process.
Exactly, and it's specified by three things, really. Some starting state, a transition function, and a reward function. Transition function, this is the world. This is kind of like the expand function, except it's a generalization of the expand function. Tells you where you go when you do something, what happens. You could think of it as a model of action. You could think of it as a model of the world. I like thinking of it as a model of the world. It's what happens. And this is the objective function, really. This is the cost function, which you're trying to optimize. It's almost like the goal, really. In fact, some people do that. Some people make MDPs where the reward is 0 everywhere except when you transition into the goal. And so to maximize reward, you better get to a goal. Otherwise, you're going to get 0 your whole life. But if you find a plan that takes you to the goal with some non-zero probability, then your expected reward is non-zero. And the more probability you have of getting to the goal and transitioning in there with a reward of 1, the higher probability you're going to get to the goal.
Is that only useful if the situation is something where the goal is the only thing you want? Like if you don't get incremental?
Oh, beautiful question. That sets up today's entire lecture. Right there. Right there. Well, it's just, and maybe I'm misinterpreting your question, so let me know if I'm not answering it. But it's like state space search, right? You got a goal test function. Like you got this expand, 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 and all the while you run this goal test function. It's like false, 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 false. True! Yay! I'm in a state where I'm rich and happy and not in jail and still married to my wife. Right there. I guess that's part of the definition of happiness. Still being married to her. So you don't get any positive reward from the goal test until you're already there. So part of the art of state space search is this heuristic thing that you get given as part of the problem, saying, you're getting warmer, bingo, jackpot. There ain't no H function here, boy. This is what you get. This is it. So you know what we're going to do? And I'm giving a little bit away here. We're going to build our own H function, just kind of, not quite like you just did on the assignment, but in a slightly different way, but we're going to build our own H. And we're going to build it out of this, because this is what we got. This is the definition of the problem right here. Any more questions about the definition of an MDP? What you get, what you don't get, what's in the box, what you have to buy separately? Accessories. We're going to accessorize our MDP with something called the value function, which is this U thing, which says how awesome is it to be in that state? What's the expected cost to go? Which is just like H. So we don't get U. It doesn't come with the problem. It's not in the box. It's outside the box. We're going to build U out of T and R. Right? I don't see no stinking U here. We got R's, we got T's, no U. R is right next to T. U is right next to T. I think T, U, V. Yeah, it's right next to T, but it's not the same. In fact, here they're right. Yeah, they're neighbors. T, U, and some people call U V, but we don't have the value function for V. Anyway, so this is kind of where we were last time. We stopped here. We knew what an MDP was, but we were helpless babes when it came to actually solving one. If your boss comes up to you and says, look, we got a certain amount of stuff in the warehouse right now, and I can tell you that customer demand over time is thus and such. So if our current state is we have X orders and we have X inventory, then if you produce a certain number of widgets by taking action, then the next state we're in, we're going to have a certain amount of inventory that depends on the orders that came in and the amount of inventory you produced. And I'm not quite sure what orders are going to come in. If you produce 10 widgets, We might have 10 more widgets, but maybe our inventory dropped by 20 because people bought 20 widgets. So our inventory might actually have gone down. This is called stochastic inventory problems, and people in the business world love them. So when you tell them that you know how to solve MDPs, they will be all over you. So you have the current state, you take action, you transition to some other state with some probability distribution. This probability distribution might reflect the uncertainty in what orders are going to come in. So you might, the state, the number of outstanding orders and the amount of inventory depends not just on your action, but on this stochastic thing that you don't control, like whoever clicks on your website.
It sounds like you're going to get a whole lot of states really quick.
Whoa, yeah, welcome to AI. State space explosion. State space explosionganza. It's just like heuristic search. So, lots of states. How do we deal with it? Exactly. State space can get big. That's why, like in the before honorable AI people came on the scene, those OR people were studying MDPs that had 4 states or 5 states or whatever, and they were doing it all by hand, and they would do small numbers. But now we want to have robots going all around, and they don't know where they are because sensors are imperfect. Just like Plato, we cannot touch reality directly. We see but reflected shadows of the flickering light. So we could be in any number of any number of states, and the problem becomes hard. So yeah, we could get a lot of states. Maybe if your company sells widgets in lots of 1,000, maybe you want to keep track of them by the 1,000 rather than individually. I talked to some military people once, and a question was asked, do you know how many bullets you own? Right? The U.S. government buys bullets, right? It's one of the things they do, and they use them up, unfortunately. And so the question is how many do we own? It's an enormous inventory problem. Not only do they not know how many they own, but it turns out that each branch of the armed forces keeps inventory in a completely different way. So apparently the Marines count them if they've already been ordered, then they're owned. Whereas the Army, it's you don't own them till they're somewhere in your possession where you could give them to some soldier or something. The notion of own is even different. So the whole question is ill-defined. That's how messy the real world is. I was trying to figure out if they would be interested in MDP solvers for inventory control. So there's a little bit of math, and you've seen this before, so now we're not as scared as we were last time. In the perfect policy, remember we can't build a plan anymore because we don't know where we're going to transition to. So this straight line of actions is not sufficient. We got to beef up our game a little bit here. We got to try and find a policy which says, I'm going to end up in some state, and when I'm there, I'd like to know what action to do. Give me policy. Tell me what to do. Think of the poor administrator who's students coming with all kinds of crazy things that students do, and the administrator needs to know what action to take. And so she looks up in her giant table, says, if you did this, then your punishment is that. Boom. We have a policy for that.
The optimal policy is the policy that if you follow it. Yeah.
You follow it, you are maximizing the expected reward that you get in the future.
Okay.
Yes, exactly. That's the definition. This is we wrote down the definition of the optimal policy. What should we do in state S? Well, we should do that action that maximizes the weighted average over all states we could transition to, weighted by the probability of transitioning to them, of this thing, where this thing is the cumulative reward we will get by acting according to the optimal policy starting from S prime.
And that U is
Ka-ching!
that starts at time 0. Right?
The first thing that we do when we get to S prime with U is we receive a reward that's not discounted because T will be 0. So we get the reward of landing in, the way we've set up MDPs in this class, you get a reward for landing in a state.
Right.
So the first thing we do is we get now we pass in S prime and we get the reward for being at S prime. And then we get the reward for being at the next state, whatever it happens to be. We have to take the expectation over all places we could end up in the future after having done whatever the actions the policy says. So this is like a very nasty, scary expression. So we're going to make life, our job now is to make this friendlier. Because this is just, it's not even obvious how you can compute that. It seems impossible. The professor is asking for the impossible. But this time he agrees it's impossible.
What's that S0 equals S?
Oh, yeah. This is sum of future rewards. And we'd like to constrain this expectation so that the first state you visited is always the one that you were asking about.
Okay.
So this is the expected sum of discounted future rewards at various states, given that you're acting according to policy pi and the first state you go to is S. Yeah. Okay, so this is tough. So how are we going to deal with this? Well, there's this brilliant guy named Richard Bellman that said, he said, okay, let's just think about this for a sec. The value we get for being in a state is the reward that we get for landing in the state plus the future reward. Now, what is the future reward going to be? Well, first of all, it's going to be discounted by gamma. If we're doing, this is the infinite discounted reward case. It's going to be discounted by gamma. And what action am I going to take? Well, obviously, I'm going to take the best one. So the value that I'll get onwards from S, looking into the future, is the expected reward after doing the best possible action. So we're going to max over all the possible actions I could take. And for each individual action, we say, okay, we take the weighted average over all states you could end up in, weighted by the probability of ending up there after taking A, of the future value we get from being in S prime. So this is totally, someone brought up the word recursive definition last time. Totally what we got going on here, right? The value of being in S is, okay, yeah, it's the reward, the immediate reward we get, plus the future. Like this is, you guys understand this because you all went to college, right? There's the future reward, which is like negative, mammothly negative. But then here is where you're graduating and getting awesome jobs and having fun and buying Lamborghinis and all those things that people with real high salaries do. This is the future. And we're going to maximize. We're going to look at what this expected value is for each action and then take the max. And of course, we have to discount it because this is in the future. And that's the value we get from acting from S. Everyone cool with the definition of U here? No, well, do you just understand what this expression means? So this is,
I'll study it.
well, it's just got two parts. It's got now and the future. For me, the mind-bending thing about this expression is that it contains U on both sides, but let's just ignore that for the moment and pretend that's okay. So pretend it's okay that it mentions U over here. Pretend that U is already well-defined before we actually get to its definition. It's just like recursion in computer science, you know. So we've got the immediate reward we get, and then we have the future reward. So, well, what is the future reward? Well, it depends what action we do. Okay, we'll take the max over all actions. Okay, for any given action, what's the future reward going to be? Well, I'll take action A. I'll end up in S prime with some probability, which is given by T S A S prime. This is the transition function. Remember, it gives us the probability that if we're in S and we do A, what's the probability we'll get to S prime? So this is the probability we get to S prime. Maybe S prime is really a problem. Maybe it's like 0.9 or something probability we'll end up in S prime. And then we'll take the we'll pretend we already know what the value is that we'll get by landing in S prime and acting from then on. All right, so this is the expected value if we do A and happen to end up in S prime. Then we take the weighted average over all possible S primes that we could end up in, and then we take the action that we take the maximum expected value over all actions. So maybe there's one action where there's a high probability that everything sucks, and then there's another action where everything's awesome. So we would like the value of taking the optimal action at S. Yeah, Frank.
Recursion usually needs a base case.
Shh.
I want to figure out the
Do you ever, in high school, they have these things called simultaneous linear equations. I don't know if you guys probably studied these, right? Like simultaneous equations, you write out x equals blah, 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 and there's like y in there. And then you have y equals blah, 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 and there's an x in there. And you're like, oh, crap! What do I do? And you like find an expression for one in terms of the other, and then substitute it in, and then magically, as long as you have as many equations as you have variables, it all works out. And I'd like to point out that we've got one of these equations for every possible S. And this quantity is, you can think of it as a variable. We have one of those for every single state. So we have one equation for every single unknown. Oh my God, it's a giant set of simultaneous equations. Now, before we get into that, though, I just want to make sure everyone understands what this says, because this is a super important equation. It's called the Bellman equation after Dr. Bellman. It's the immediate reward. Like, how awesome is state S? Well, that depends on the reward we get when we land in it and the reward we can get in the future. The reward we get in the future depends on the states we go to, and the states we go to depends on what action we take. So I'm not sure which action I'm going to take yet. Let me evaluate each one individually. So I'll calculate this for action 1. I'll calculate this for action 2. I'll calculate this for action 3. And I'll take whichever value is the greatest, because that's the action I'm going to have as my policy for being an S. I'm going to have whatever the A is that maximizes this.
How come there's no policy for that U? Because I noticed the other U's have policies.
We don't have a policy yet here. In fact, what policy is being implicitly assumed by this U?
Yeah.
Which one is it?
The optimal? I don't know.
It's the policy where we take the action that maximizes this expression. And that is the optimal thing to do, right? The optimal policy is the one where we maximize the expected future reward. U is the expected future reward.
So that is U.
So this is assuming, this is U pi star.
Okay.
Yeah. Dan.
dumb, but is there a way to draw this?
There's one guy that draws it in a way that I think is not very helpful and would take a long time to explain, and I don't even remember. So we're not going to do that. Do you know what an MDP is? Did we get that? I tried to draw a little picture last time about what an MDP was, and I think, oh, where's my, this doesn't look good. Wow, that doesn't look good at all.
Maybe exposure is set to 0.
Huh. Wow, that's a first for me. I don't remember this program totally crashing before. Let me just restart it. No problem. Windows, if I just say open, is that going to be enough? Yes, it is. How about that? Yeah, I'm not a huge Windows fan, I have to say. Okay. So this was my attempt to draw an MDP. And were you cool with this picture here, where we've got a state, and then you take an action like A, and you could end up in state 47 or state 13, or you could do action B, and there's some probability you'll end up in 47, and some other probability you'll end up in state 7. Those are two separate actions. So you got what an MDP is, more or less?
Yeah, it makes sense.
Okay, so it's just the equation part of it that's spooking you for the moment.
Yes.
Okay. So ignore this middle line, because I think I agree that's a little confusing. Let's focus in on this definition of the value function u. Or you could call it, the book I think tries to call it u because you could call it a utility function. It's the utility of state S. How wonderful is state S? It's a lot like a heuristic function. In fact, it's exactly the heuristic function. It's the expected reward you're going to get in the future from landing in S and acting optimally from then on.
It's a heuristic function, except it deals with probability, so it's not definitive.
It's not definitive?
Like,
Is that what you said?
yes, like,
Well, yeah, it's the expected reward.
yes.
Yeah, because we're in an MDP. I mean, life is uncertain, right? I buy a lottery ticket. What's the expected reward? Like, there's some teeny probability I get $1 million and a large probability that I just lost $1. What's the expected utility? It's probably like, I don't know, minus 3 cents or something. It's probably the expected utility of buying the lottery ticket. I don't really know, but I'm guessing it's slightly negative because I think they make a lot of money.
Well, if they're giving away a lot of money, they're making a lot more.
Yeah, yeah. So, so you understand expected utility at an intuitive level, and that's just what we're computing here. We're computing expected utility. In an MDP, there are two sources of utility. There's the immediate utility, and then there's the future, the reward you get in the future. So I can try and draw on a piece of paper.
It just seems like
We'll see if it. I'm just not guaranteeing it's going to make any sense. So we're wondering. So like when we reach some state S, we get a reward. So how do we draw that? There's a just giant drop of money coming out. So woo, we land in state S. Oh, I got reward. Awesome. But now I'm not dead. I can take more actions. So I have the potential of getting more reward in the future. It might end up being negative reward. We'll see. Now there are a bunch of different actions I can do in the future. I could do action A, and that can take me to this state, which might have, so if that's S, let's call this S2, and maybe this has a U of S2 equals like 5, and it gets there with probability 0.5. And with probability 0.5, it gets to this other state that, let's call it S3, and maybe U of S3 is 3. So the expected utility of taking action A, right? This is T of S A S2 equals 0.5. And here we've got T of S. We were in S, we did A, and we got to S3 with probability 0.5. The expected utility of U of S equals whatever reward we get. Let's say, what did we get here? $2. 2 plus, and now we're doing a maximization over actions. Well, let's see. If we do action A, we ended up with 0.5 chance of getting reward 5 and 0.5 chance of getting 3, which equals 4. So the future reward of doing action A is 4. There might be some other action B. Maybe if we do action B, there's a 0.5 chance that we go over to S2, and I don't know, maybe there's some hellish state here, like S4, and there's a 0.5 chance we'll end up in S4, and the utility of S4 is like -10. So if we do action B, with 0.5 we get 5, and with 0.5 we get -10, and that ends up being like, sorry? Yeah. So we're going to take the max, so that means we're going to take A, so that means it's 2 plus 4 equals, oh well, there'll be some discount factor here, like 0.9. So 0.9 times 4 is 3.6, so this is going to be 5.6. Did that make any sense, Dan?
It makes sense, but the problem I have is, well, actually there's two.
Okay.
One is for the U of S2, you don't necessarily get it as 5. You just
Oh, okay. So you're caught up in the recursion problem here.
Yes.
Let's pretend, yeah, that's so that's really tricky, isn't it? How do we know U of S2? Because by God, there could be an action we do at S2 that actually gets us back to S. So, whoa, mind bender. So, in order to make ourselves feel better, let's pretend that we know all the U's except for the one at S. And I'm going to tell you how we deal with that in reality in a moment. Okay, but for the moment, let's live in fantasy land, and we just don't worry yourself that this is an enormous set of simultaneous equations.
Can you explain what was it you called it, the line with the 5.6,
Here?
yeah, the
Um,
0.9 value.
Oh, that was gamma. That was our discount factor.
Can you explain that?
Why do we have discount factors? So there are two answers to that. So let's go back to, please go back. Why am I getting the little spinning circle? I don't like that. Oh my. So there are two answers. The practical answer is we do it because otherwise, if we talked about total future reward out to infinity, it would be infinity, and then all policies would look awesome, and what's the point of thinking about what to do? Another way of thinking about it is that the world changes, for example, or it might be uncertain, and so future rewards we get in the future are somehow less certain, and so we'd like to optimize the nearer ones more.
The discount is less for the next, or is
Future actions are discounted more.
Right.
It's like 0.9 to the third is like, we're talking to small numbers. I mean, it's decaying exponentially. So the future actions are exponentially less important. You can also, if you're trying to sell this to your boss, you can talk about things like inflation or net present value. I don't know if you know any of these financial terms, but it's better to have money now than in the future, because if you have money now, you can put it in the bank and get interest, for example, or invest it somehow and get a return. So gamma is like the inverse of the return you might otherwise have had for your money. So getting money now is always better than getting it in the future. Yeah. Oh, great. PDF is back. So here this is, some people talk about total reward, in which case they usually have a finite horizon. Like they say, okay, you're going to live for 3 steps.
okay.
So we got the reward, you get it the first state you visit, the second and the third, and we're done. And okay, we can optimize over that. That's not going to diverge to infinity. If you want to go out to infinity, then talk about the best thing to do in general, then we really need this discount factor to keep it from blowing up.
So, what was the Greek letter used for that?
Gamma.
Gamma.
This little curly guy.
Gamma cubed for the S.
Yeah.
The next one.
Yeah.
Okay. Is that
Where this is just the state we happen to visit next. The state we happen to visit after that. This isn't meant to be like S1 always has gamma. It's just
right? Gamma at the next state.
yeah, the state we happen to visit next. Yeah.
And is it always incrementing exponential?
Yeah. That's the discounted reward model. That's the one we're going to use. Yeah. Nathan.
On the next slide,
Yes, sir. We're talking here?
The E function.
Oh, this, okay.
Yeah, which variable is the random variable? Because don't you need a random?
Yeah, that's why this question is kind of hard to read. The S's are.
Okay, so all the
Because we don't know exactly where you're going to end up.
Okay.
So we want to take the expectation over all possible future trajectories weighted by the probability of that trajectory.